Welcome back, everybody. Today I'm going to be completing homework 4, part A for process dynamics controls. And today we're going to be deriving the transfer function relating the change in height in a manometer to the pressure differential, assuming that the viscous dampening can be expressed in terms of the pressure gradient with laminar flow, meaning that our fanning friction factor is going to equal 16 over our Reynolds number. So getting started here, I'm just going to go ahead and draw us a simple schematic of a manometer. So we got our U-shaped tube here. We've got a liquid level here and a liquid level up here. And then between them, we've got our height difference. And if we balance out the forces on a manometer, we know we've got three things going here. So overall, with the forces, we are, of course, going to have gravity acting on our manometer. And we're also going to have our atmospheric pressure acting on our manometer. And finally, we're going to have our viscous dampening pressure acting on our manometer, acting on the level as it moves downward. I'm just going to call this our viscous pressure. Now, how are we going to define each of these variables? Well, we'll start off with gravity. We know our gravity is, of course, going to have our gravitational constant G. And then we also need to consider how gravity is acting on our manometer. So, assuming we've got this force here, that means coming over to this side, gravity is essentially acting up here. And for this analysis, we're going to consider downward forces to be positive and upward forces to be negative. And since gravity here is an upward force, we're going to put a negative sign in front of it. We know that force must always equal mass times acceleration. So we've got our acceleration here, but how are we going to get our mass? Well, for the mass that gravity is acting upon, we're looking at our height. So we've got our G times our H times our A. That gives us our volume that gravity is acting upon. And then to get that in the form of mass, we're going to multiply it by the density of our liquid, rho. So for our gravity term, we're going to have a negative G times H times A times rho. And then for our atmospheric pressure term, this is also fairly trivial. We've just got our pressure, which is acting down on the manometer, our atmospheric pressure. So it's going to be positive. We're going to have a plus our P, and then of course we know that pressure times area equals force. So for our atmospheric pressure term, we're going to have a plus P times A. Now it gets a little more difficult when we're looking at our viscous pressure. So for our viscous pressure, we determined for the scope of the problem, we can express the viscous dampening in terms of our delta P over rho. And we know that this, for the laminar regime, is going to equal 4 times our fanning friction factor times L over D times our average velocity squared over 2. Now for the rest of this analysis, I'm going to go ahead and drop that average on our velocity just so we're not having a bunch of subscripts, but this is our overall equation that we're starting out with. And the first simplification we're going to make here is that we know that our fanning friction factor F is going to equal 16 divided by our Reynolds number for our laminar regime. And then we're also going to say that we know our Reynolds number for a tube is going to equal our viscosity mu divided by our rho times our average velocity v times our diameter d. And plugging both of these into this expression gives us that our delta P over rho is going to equal, so we've got 4 times 16 divided by 2, it's going to give us 32 times our L times our V squared times our mu, all divided by our rho times our velocity times our diameter d squared, as we've got it both in this Reynolds number term as well as our original viscous pressure term up here. Then we can go ahead and cancel a couple things. As you can see, our densities here, our rho's cancel out. One of our v's up top cancels out, which leaves us with the expression delta P equals 32 times L times V times mu over D squared. To simplify this down even further, we're going to multiply each side by the area, as we know that we're going to need this in this form anyway, as our force, again, equals our pressure times our area. So multiplying this both sides by the area, and then substituting out our area, as we know that our area is going to just equal our pi times d over 2, i.e. our radius squared, or pi r squared. If we sub that in to our expression right here, we get times pi d squared over 4. And then as you can see, our d squareds cancel. If we multiply this all out, what we get is that our delta P times A is going to equal 8 pi times L times mu. And then the last simplification we're going to make here is that we know that our velocity is our change in height over our change in time, i.e. our dH dt. And that's going to be important when it comes to finding our final transfer function. And the last thing we're going to consider for our viscosity is that, like our gravity, it is also acting against our pressure, which is pushing down. So we can call our viscous pressure a negative term as well, as it is acting up against our pressure pushing down here. So if we combine all of these, we get that our forces are going to equal negative G times H times A R rho plus our pressure times our area minus our 8 pi times L times mu dH dt. And then finally, we need to consider that on the other side, on our left-hand side of our equation here, we know that the overall forces are going to equal the overall acceleration times the overall mass. And the overall acceleration can be expressed by d squared h dt squared times the length, the entire length of our liquid in here, times the cross-sectional area, giving us our volume, of course, times the density, our rho, which gives us our total acceleration times our total mass in our manometer. We're going to set that equal to our negative, so I'm just going to sub out this F up here, setting that equal to our negative G times H times A times rho, and the rest of our right-hand side, so either D squared H over dt squared times L times A times rho, and equal that all over there. And then, as you can see here, we've kind of got the form of a general differential equation here, so we're going to get it into more of the conventional terms, so that we're going to be able to take a Laplace transform on this. So what that's going to give us, if we divide over our L times A times rho, we're going to get d squared h over dt squared plus, taking all of this over, and have eight pi mu over our area times our density, all times dH dt, and our final term is plus our G, divide out that rho, times H over L I'm going to pull this H out of here, plus our G over L times our H, as those two cancel. And that's all going to equal our 1 over rho times L times our P. So now we have this in a differential form. We're going to be able to take a Laplace transform. So I'm going to go ahead and do that. So taking our Laplace transform of this function, we're going to get, so we've got dH squared dt over dt squared. That's going to give us our big H times s squared plus And then we're going to call, before we move on to our Laplace transform, we're going to call each of these constants in front of our differential terms. So we're going to call this 8 pi mu over a times rho. We're going to call this beta. We're going to call this g over L. Gamma. We're going to call this 1 over rho times L alpha. So we're going to have this h, big H s squared plus big H times beta s plus big H times r gamma. That's going to equal r alpha times r big P with a line under it as it's already capitalized in the original function here. And then we're going to rearrange this function a little bit to get our overall transfer function. So first things first, we're going to isolate our h. We've got h times s squared plus beta s plus gamma equals alpha times r p. And then if we divide this all over, what we get is that h, big H, is going to equal r alpha all divided by r s squared plus beta s plus gamma times r pressure. And that right there is going to be our transfer function for our manometer. So now we're good to go ahead and move into the next part of Part A for Homework 4. Before we move into the simulation of an actual manometer in Python, we need to get our second order manometer transfer function to the general second order transfer function form, which is our GP equals K over tau squared S squared plus 2 zeta tau S plus 1. So to get it into this form, first thing we need to do is divide over by gamma, as we're going to need that plus 1 at the end of this term here. So that's our easiest starting point. So that'll give us our gamma over, or our alpha over gamma divided by 1 over gamma plus 1 over gamma s squared, I should say. S squared plus beta over gamma times s plus 1. And then, as you can see here, in this case, you can see this 1 over gamma is where our tau squared should be. So we can say that tau squared must equal 1 over gamma, meaning that tau must equal the square root of 1 over gamma. If we sub that into our expression, we get that alpha over gamma over square root of 1 over gamma squared times s squared plus beta over gamma times s plus 1. So we've got this first term in our denominator, how it should be. What we need to consider next is this next term. So you can see our beta over gamma is currently, rewrite this somewhere else. This is an unfortunate spot. I'm just going to go through each variable actually before we sub these in, just so I don't have to write this a bunch of times. We know that our beta over gamma is going to represent 2 times zeta times tau. So if we rearrange this, what we get is that our zeta value is going to equal beta over 2 times gamma times tau. And if we sub in this tau that we figured out up above, we get this zeta is going to equal beta over 2 times gamma times the square root of 1 over gamma. It's all perfect. So now we should have all of the variables we need here to sub back into this expression up here, which is going to give us alpha over gamma divided by square root of 1 over gamma squared times s squared plus 2 times r beta over 2 times gamma times gamma to the negative 1/2, which just gives us gamma to the 1/2, we cancel that out, times our tau, which we've said is gamma to the negative 1/2, plus 1. I believe we can simplify this down even further. But we do not want to in this case. Times s. Forgot our s here. So now you can see that we have transformed our manometer transfer function into the form of this general second order transfer function, where our alpha over gamma, that is going to be our k, our 1 over gamma, that's going to be our tau, and then our beta over 2 times gamma to the 1/2, that is going to be our zeta value. Here, yet again, we've got our tau, and then our plus 1. While when h is our GP, that checks out. So here is transfer function. In the form, we're going to be able to do some Python work with it. So now let's go ahead and move on to the next part of part A.
All right. Now that we've figured out our transfer function for our manometer and then put it into our general form for our second order transfer functions, we can go ahead and simulate a water-filled manometer where the total length of the fluid is 1 meter, its tube diameter of the manometer is going to be 1 centimeter, and we're going to determine the gain, damping coefficient, and time constant. We've already done that up on the board. That's our tau. Our tau is our time constant. Our gain is our k, and our damping coefficient, that's our zeta. That's what we've defined all three of those variables up on the board. So now we're good to go ahead and simulate this with a 5,000 Pascal step change in pressure. We're going to see what our system does. So first things first, we're going to go ahead and put in all of our variables that we know here. So we know that our length of our fluid is going to be 1 meter. We also know that our tube diameter, our D, is going to be 0.01 meters. It's 1 centimeter. What else do we need here? We know that our gravitational constant G is going to be 9.8 meters per second squared. We also know that we're going to need our rho, our density of water, which in this case, I think we're going to call it 1,000 kilograms per meters cubed. We also need our mu, which is our viscosity, which I believe is 1 E minus 3 kilograms per meters second. I believe that is all correct. So now we can go ahead and put in our alpha, our beta, and our gamma values right after we put in our area, as well as we're going to need that for all of our values. So our area is going to equal np dot pi times, so we got pi r squared, so that's going to be d squared divided by 4. Pi times our d squared divided by 4. Yep, that should be our area. So now we can go ahead and start out with our gamma. So our gamma is going to be, if I remember from up on the board, our gamma is our gravity divided by our length value. And then moving on from there, we've also got our alpha on the other side of our equation, which I believe is 1 divided by our g times our rho. That sounds about right. And then last of all, we've got beta, which I remember correct, that is going to be 8 times r pi, which this is also not g, this is L. Eight times pi all over our rho times our area. And I think that's all of our constants we had in our initial transfer function. We also had a times mu up here. Perfect. All right. So now that we've got our gamma, our alpha, and our beta, we can go ahead and kind of normalize those into our general transfer function. As we discussed up on the board here, we can define our time constant tau, our controller gain k, and our damping coefficient zeta, all in terms of these 3 constants that we figured out here from our initial transfer function. So we'll start out with our k, as that's nice and easy. That is just our alpha divided by our gamma, I believe. Yep. Alpha divided by gamma. Perfect. And then we'll do our tau, which I believe is the np dot square root of 1 over our gamma. Look up here. Is that how we define tau? Yep. Fantastic. And then our last variable, that is our damping coefficient, that's our zeta, which we defined as our beta. What else we got up here? Beta divided by 2 times our alpha, no, our gamma to the 1/2, power of 1 over 2. And I believe that is all of our coefficients we're going to need to put in our transfer function, our general transfer function. So hit a Shift Enter. Looks like that is all good. So now we can go ahead and define our overall transfer function. So we're going to say that our GP, our general transfer function, that is going to be equal to our K divided by our tau squared times our S squared plus our beta, wait, no, it's going to be plus 2, we got up here, 2 times our zeta times our tau times S, all plus 1. Fantastic. There's our general transfer function. So now we are good to go ahead and simulate this out. So we can say that our T and our H is going to equal to our simulation of our GP. And then we discussed in the initial problem statement how we're going to have a 5,000 Pascal step change in our pressure. So we're going to define that now by saying our lambda, our step change, lambda, there we go. T is going to be 5,000. That's going to be our 5,000 Pascal step change. Then we're going to have n equal to 1,000, and our dt, time step, I'm just going to set that equal to 0.1. Fantastic. So now we're good to go ahead and make our plot and discuss the implications of that plot. So we're going to do our usual fig equals make subplots. We're going to do a fig dot add scatter. We're going to have our x is going to equal our t, our y is going to equal our h, our height, and our mode will be lines. And I believe that's all good. Let's go ahead and hit Shift Enter, see what we get. Fantastic. So you can see here, we're starting out in our manometer. We're jumping up to about 1 meter, and then we're oscillating back down to up to 0.9 meters, oscillating back down to 0.1 meters, and then we're going up and down, and then over time, over a fairly short amount of time, we do see that we stabilize out at exactly where our height would be on our manometer. So I believe that is the end of this part of part 1. So go ahead and move on to the next one.
Now, moving on to the next one, we're going to show algebraically that two systems with first order transfer functions in series will always have a dampening factor zeta greater than 1 and thus will always be overdamped. So let's start out by defining what two first order transfer functions in series would look like. So we'll recall that a first order transfer function takes on the form k over tau s plus 1. If we have two in series, we're going to have a k1 over tau 1 s plus 1 times a k2 over tau 2 s plus 1. And if we multiply these out, what we get is something that looks very similar to our second order transfer function general form. So we get tau 1 tau 2 s squared plus tau 1 plus tau 2 times s plus 1. Which looks really similar to our second order function, which is just going to be a k over tau squared s squared plus 2 times r zeta tau s plus 1. as we can see here, as we've done previously, we can define our tau in our second order system as the square root of tau 1, tau 2. It's tau squared equals that tau 1, tau 2. If you take the square root, you get this right here. Then we can also say, as we've done before, that 2 zeta tau is going to equal tau 1 plus tau 2. And then if we divide a couple things over and then sub in our tau over here, what we get is that our zeta equals tau 1 plus tau 2 all over 2 times, and I'm going to change the color up for reasons I'll explain in a second here, square root of our tau 1 times our tau 2. You'll notice here that we've got both the geometric mean, which is our square root of tau 1, tau 2, as well as the arithmetic mean, our tau 1 plus tau 2 over 2. And we're going to be able to prove that our arithmetic mean is always greater than our geometric mean. And if that is the case, then our arithmetic mean times 1 over our geometric mean will always be greater than 1. So let's go ahead and prove that real quick, even though that's an assumption that we know is true. We'll go through and prove it so that we can know for a fact that two first order systems in series will always be overdamped, because that zeta is always going to be greater than 1. So pulling forward with that proof, like I was saying a second ago, we said that our tau 1 plus tau 2 over 2 will always be greater than or equal to the square root of tau 1, tau 2. And then if we go ahead and square both sides, we get that tau 1 squared plus tau 1 tau 2 plus tau 2 squared, all divided by 4, is going to be greater than or equal to tau 1 times tau 2. If we multiply over that 4, what we get is that tau 1 squared plus 2 tau 1 tau 2 plus tau 2 squared equals 4 tau 1 tau 2. Oh, not equals. Is less than or equal to 4 tau 1 tau 2. And then if we subtract this over, what we get is that tau 1 squared minus 2 tau 1 tau 2 plus tau 2 squared must be greater than or equal to 0. And then if we factor that out, we get that tau 1 minus tau 2 squared must be greater than or equal to 0. And we know for a fact that this is true because anything squared must always be greater than or equal to 0. So what we've done here is that we've proved that the arithmetic mean must always be greater than the geometric mean, meaning that our zeta since our zeta equals our tau 1 plus our tau 2 over 2 times our 1 over our square root of tau 1 tau 2. If we know that this value is always going to be greater than this value here, we've got something greater over something lesser, which will always be greater than 1, meaning that our zeta must always be greater than 1, which farther means that two first-order systems in series will always be overdamped because our zeta will always be greater than 1 by this algebraic proof here. So now you can go into Python and do something similar to this computationally. So let's go ahead and move on to the next part of part A.
All right. Welcome back to the last part of part A for homework 4 for process dynamics and controls. And in this last part, what we're going to be doing is we're going to computationally simulate the behavior of a second order system for different damping coefficients for oscillatory inputs at frequencies below, at, and above the natural frequency. So to do this, well, first I need to define what the natural frequency is. So for a system, the natural frequency, which is often called omega n, is just 1 over the time constant tau for any given system. So that's the definition of the natural frequency. And to simulate what happens when we change that natural frequency up, what we're going to need to do is redefine our k, our tau, and our zeta. So first we're just going to say a k equals 1, not as integer, a tau equals 0.5, a zeta equals 1. And then our natural frequency is going to be that 1 over tau. And then we're just going to copy down our transfer function that we defined up above here. Perfect. And then finally, we're going to just copy down exactly what we have right here to make our plots. Except we're going to change something up. Instead of this 5,000 Pascal step, what we're going to do is we're going to take the mp.sine, because to analyze this, it's useful to utilize the sine function of our natural frequency times our t here to vary that frequency. And we're just going to observe what this looks like initially. So as you can see, we've got what looks like a sinusoidal function going up and down here from -4 up to 0.6 here. So let's see what happens when we alter this this frequency factor. So if we go above the natural frequency, we'll say below times 0.5. Let's see what happens. As you can see, we start to get wider. It starts to widen out, and the amplitude starts to increase a little bit. So let's say 0.01. See what happens. Then I think I've gone a little too far here because now we're not even seeing the oscillations at all. So let's say 0.1. Here we go. As you can see, we're getting much wider here. And then let's check at above the natural frequency. And you see our amplitude decreases and we get much tighter oscillations here, which makes sense because we're altering the frequency. So obviously, the lower the frequency, the wider your oscillations are going to be, and the higher your frequency, the tighter they're going to be. So past that, well, we also asked for a different damping coefficient, so different zetas. So let's go back to our Wn equals just 1 over tau, our standard natural frequency. And this time, let's bring our zeta up to 2. See what happens. Not a whole lot at the natural frequency. What if we bring it up to 5? As you can see, the shape does not really seem to be changing. The frequency is staying the same, but the amplitudes are changing somewhat. But when we're at that natural frequency, our frequency doesn't change based off of the damping coefficient. It only changes based on that natural frequency, which makes sense because it is a frequency value. So I think that is the end of our homework for part A. I will see you in the next one, part B.